Have you ever just looked around and wondered what all this stuff is actually made of? I mean, your phone, the chair you're sitting in, the air you're breathing. It turns out the universe is built from a surprisingly simple recipe, and today we're going to break down the key ingredients. It's a huge question, right? But the answer is honestly one of the most amazing discoveries we've ever made. If you could zoom in, and I mean way in, past anything a normal microscope could see, what would you find? You'd find these guys, atoms. These incredible little structures are the foundation for, well, everything. And the best part is, they follow a few basic rules to build the entire complex world around us. So, what are those rules? Let's dive in. Okay, our journey begins at the very heart of matter itself. We're going to shrink ourselves down, go right inside the atom, and meet the particles that make it all happen. So, here's the basic layout. Think of that like a tiny solar system. Right at the center, you have this dense core called the nucleus. And then zipping around that, you have these even tinier particles called electrons. But they're not just flying around randomly. They're very neatly organized in layers, which we call shells. And the whole thing is made of just three key players. In the nucleus, you've got your protons, which have a positive charge, and neutrons, which have no charge. They're neutral. These two make up almost all the atom's mass. Then, in those outer shells, you have the tiny, negatively charged electrons. Now, they might be small, but trust me, they're where all the action happens. And those electrons have some very strict rules they have to live by. They fill up the shells from the inside out. That first shell, closest to the nucleus, is pretty small. It can only hold 2 electrons tops. After that, the next 2 shells can each hold a maximum of 8. This simple setup is the absolute key to understanding everything else.
So we know the parts, but how do these pieces tell us what kind of atom we're dealing with? What really makes an atom of gold different from an atom of oxygen?
Well, believe it or not, the answer is just one thing: the protons. The number of protons an atom has is its unique fingerprint, its atomic number. If it has 6 protons, it's carbon, every time. If it has 79 protons, it's gold. This number is what defines the element, and it never, ever changes.
Now, while the proton number is set in stone, an atom can play around a little with its neutrons. When you find atoms that have the same number of protons, but a different number of neutrons, you've got yourself some isotopes. It's the same element, just a slightly heavier or lighter version.
Carbon is the perfect example here. Every carbon atom in the universe has 6 protons. But most carbon, what we call carbon-12, has 6 neutrons too. Then there's the famous one, carbon-14, which we use for dating ancient artifacts. It's still got 6 protons, but it's packing 8 neutrons. Same element, just different flavors. Okay, so we've got the single atom down. Now let's zoom out and look at how we organize all these different types of atoms. This brings us to probably the most important chart in all of science. This is the periodic table, and you have to admire the pure genius of Dmitry Mendeleev, who created it back in 1869. He didn't just organize the elements they already knew about. Get this, he left blank spaces for elements that hadn't even been discovered yet, and he predicted what they'd be like. And you know what? He was right. Mind-blowing. Learning to read this table is easy once you know the code. It's organized by atomic number. That's the proton count. The rows are called periods, and every time you start a new row, it means the atoms have another electron shell. But the columns, the groups, that's where the magic really happens. The group number tells you how many electrons are in that all-important outer shell. And those groups aren't just for keeping things tidy. They're basically families. Elements that live in the same column behave in very similar ways. You could say they have similar chemical personalities. Just look at this contrast. Over on the far left in Group 1, you have the alkali metals. They have just 1 electron in their outer shell, and they are desperate to get rid of it to feel stable. This makes them incredibly reactive. Now, go all the way to the other side, to the noble gases. Their outer shell is completely full. They're perfectly happy, totally stable, and they just don't want to react with anything. And that's the big takeaway here. It's all about those outer electrons. An element's entire personality is driven by its need to get a full outer shell, whether it does that by giving electrons away, stealing them, or sharing them. That's what powers all of chemistry. You know, it's amazing to think that we didn't figure this all out overnight. This picture of the atom was pieced together, bit by bit over many years, by brilliant scientists building on each other's work. Our idea of the atom has changed so much. We started with Dalton thinking they were just tiny, solid balls.
Then J.J. Thomson discovered the electron and came up with a plum pudding idea. After that, Rutherford found the dense nucleus, Bohr put the electrons into those specific shells, and finally, Chadwick discovered the neutron, which really completed the model we use today. Each step brought the picture into sharper and sharper focus.
So when you look at the periodic table, you're not just looking at a chart, you're reading the ingredient list for the entire cosmos. It's a story of discovery and the toolbox that has allowed us to build the modern world. The only question left is what will we build with it next?